Welcome to the Kentucky Watershed Academy's presentation on mining best management practices for water quality. The expansive coal mining operations in the landscape can have a profound impact on water resources, both within the immediate area of activity and well downstream of it. It also has created large areas of flatland for development and wildlife habitat in the mountainous regions of eastern Kentucky. Schools, industry, and airports are some of the uses that have been made on abandoned mine lands in Kentucky. Post-mining lands have also become wetland areas for waterfowl and habitat for reintroduced native elk species. Resource extraction, primarily coal mining, is conducted in the far western and eastern regions of the state, so these best management practices will be most relevant to watershed professionals in these areas. There are many types of mining, but the main two categories employed in Kentucky are surface mining and underground mining. The mining method is largely dependent on the geology of the coal deposit. Surface mining is employed when the coal deposit is obviously near the surface of the land. This type of mining can recover larger percentages of coal seams and can cover broad expanses of land using a variety of large-scale equipment, such as shown in this graphic. The general surface mining process includes the following steps. The overburden of rock and soil is broken up using explosives, then removed using drag lines or by a mechanized shovel and truck. Once the coal seam is exposed, it is drilled, fractured, and mined in strips. The coal is then loaded onto large trucks or conveyors to be carried away to a coal preparation plant or for direct use. As part of the rehabilitation and reclamation process, the stored overburden and soils are replaced to approximate original land contours while mining is ongoing or soon afterward. The soils may then need to be ripped to reduce compaction before planting with grasses, trees, or other vegetation. Mining activities can have varied and long-lasting impacts on water quality. Drainage from mined lands can contribute high levels of metals such as iron, manganese, aluminum, arsenic, copper, and lead to receiving water bodies. These metals and other contaminants can raise the conductivity of the water, harming aquatic life. The oxidation of ferric sulfide and other substances can result in acid mine drainage with very low pH levels. A low pH is harmful to aquatic life as well as other life forms that come in contact with the water. Sulfate is also typically associated with coal resources in Kentucky, and runoff from mine sites can carry higher concentrations into waterways, where it can bond with the water to form sulfuric acid, further lowering the water's pH. High sulfate concentrations can also cause drinking water to have a bitter taste and may have a slight laxative effect. And other animals, such as cattle, are sensitive to high levels of sulfate in the water. And like construction and forestry operations, mining typically disturbs large areas of soil and sediment that can be carried to nearby waterways. This table, taken from a US EPA document, lists categories of mining activities with some of the expected pollutants and their sources. Dust, total suspended solids, turbidity, and pH are common to most of the activities. Oil, fuels, and other chemicals are contributed by equipment use and maintenance activities. There are many laws that apply to coal mining activities, but we will just cover a few of the more important ones that relate to water quality protection. The Surface Mining Control and Reclamation Act was passed in 1977 with the dual goals of promoting coal mining to provide the country with this fuel source while also minimizing the environmental impacts of the mining process. SMCRA, as it's called, addresses erosion and control measures as they relate to hydrologic balance, sediment control, and water discharges. In Kentucky, the Division of Mine Reclamation and Enforcement is responsible for inspecting all surface and underground coal mining permits of the state to assure compliance with SMCRA. It's helpful to note that DMRE, the Division of Mine Reclamation and Enforcement, is also responsible for regulating and enforcing these laws for non-coal mining sites in the state, including limestone, sand, gravel, shale removal, and the surface effects of dredging river sand and gravel. Coal mining permit applications to Kentucky's Department for Mining Reclamation and Enforcement must include a mining and reclamation plan. A Clean Water Act Section 404 permit is frequently required from the U.S. Army Corps of Engineers since it's needed for most proposed discharges of dredged or fill materials into waters of the United States. And when these 404 permits are required, a state-issued 401 permit is also needed. The 401 Water Quality Certification Program ensures that activities which require the federal 404 permit are also consistent with Kentucky's water quality standards. In the case of mining, the Energy and Environment Cabinet has authorized the Department of Natural Resources to issue individual water quality certifications related to surface coal mining operations. And when mining operations result in permanent stream loss, a stream restoration or mitigation plan must be submitted to the Division of Water. When the proposed disturbances include 1 acre or more of jurisdictional wetlands, a wetlands mitigation plan is also required. Finally, the Kentucky Division of Water is responsible for reviewing and issuing KPDES, or Kentucky Pollutant Discharge Elimination System permits for mining. These require a BMP plan, and its components are described in the accompanying permit. In the case of mining, DMRE conducts the associated mining for the KPDS permit compliance and then notifies the Division of Water if there seem to be any discharge violations. The Division of Water is then responsible for investigating and enforcing the permit. The 1990 Kentucky Surface Mining Law and related regulations require that mining permit applications also contain a mining and reclamation plan. This plan includes sections covering topsoil handling, backfilling and grading, spoil disposal, acid and toxic material handling, surface and groundwater control, and monitoring and revegetation. Each of these sections contains associated best management practices that the operator intends to use. The terms of the mining permit must be met throughout the mining process, including site preparation, mining and reclamation, and the 5-year period of extended responsibility. In 1996, Kentucky developed a guidance document for best management practices to protect water quality from mining land uses. This document is still in use today and recommends a variety of structural and non-structural practices to control pollution from related debris, sediment, and acid drainage. A central tenet of this document states that the best way to prevent pollution of streams with debris, sediment, and acid drainage is to keep rainfall runoff and groundwater away from these materials or substances. The BMPs that follow relate to this overriding concept. Woody debris results from site preparation before mining occurs. Clearing and grubbing refers to the removal of trees and brush from the land surface to allow equipment to access the coal layers beneath the ground. The resulting debris is typically chipped for mulch, burned or incinerated, or may be stacked in windrows to be composted, as shown in the photo on the right. It should not be placed in stream beds where it will likely alter water flow and quality. The main sources of sediment and soil erosion associated with surface mining include haul and access roads, areas of active mining, areas being cleared for mining activities, and areas in the process of reclamation. As with any activity involving soil disturbance, it's best to think of prevention through the use of erosion control measures. This reduces threats to water quality, reduces the need for more costly reclamation or restoration, and prevents a valuable natural resource, soil, from becoming a pollutant. Acid mine drainage results from a process similar to that of rust forming on an iron screw. When the iron is exposed to water and air, it rusts. Pyrite, or fool's gold, is a mineral commonly found in mines that contains iron and sulfur as ferric sulfide. When it is exposed to water and air, it forms the orange-colored iron hydroxide, as well as acidity as hydrogen ions and sulfate. Elevated sulfate levels are often found in acid mine drainage discharges. Sulfate can bond with water to form sulfuric acid, or it can attach to calcium to form a gypsum sludge. In these graphics depicting the AMD formation process, you can first see that pyrite is buried beneath layers of stone, dirt, and coal, until mining exposes it to air and groundwater. Iron hydroxide shows up as an orange sediment that coats the bottom of streams and limits light penetration into water. It can smother aquatic life and destroy stream habitat. Acidity, or a lowered pH, can be toxic to aquatic organisms and may cause other metals to dissolve more readily and become available. For instance, clays are typically high in aluminum. When clay is dissolved by this acidity from acid mine drainage, it can release aluminum into the runoff water. This appears as a white solid and may be visible as a coating on rocks or cloudiness in the water. Aluminum can also be toxic to aquatic life. This slide shows other erosion control measures that are used on mining sites and common to general construction activities. From the top left, we see sedimentation ponds, which are water detention storage structures designed to detain storm flow. These enable the removal of settleable solids from runoff and collect runoff flows for point source discharge. They should be located immediately below the disturbance and out of perennial streams unless otherwise approved in a permit application. Channel protection, including check dams, are measures used to stabilize channels against erosive forces. These runoff channels can be lined with grass, rock, riprap, or concrete. They can also be protected with check dams to reduce the velocity of stormwater runoff flows. Dams can be constructed of straw bales, lumber, or rock. However, straw bales are not generally recommended due to their tendency to decompose and fail. Silt fences. These are temporary sediment barriers constructed of a semi-permeable fabric that is stretched between and attached to supporting posts. They trap sediment while allowing runoff to pass through the fence. Silt fences can be effective in short-term erosion and sediment control, especially during the construction phase of other control structures, haul roads, or in small drainage basins. These fences need to be properly installed to prevent failure, which includes placing them along the land's contours to capture flows and installing the stakes on the downhill side of the fence and burying the fabric and stakes in about 8 to 10 inches of dirt. Finally, vegetative filters are temporary or permanent sediment traps of cultivated or naturally occurring vegetation. These are also familiar to you as riparian zones, grass filter strips, and stream buffer zones. They provide areas for the deposition of runoff pollutants before they reach the drainage ways. In mining areas, these are best employed in areas of moderate slope that receive sheet flow from storm events.
Some mine drainage is inevitable, so we'll now move on to controls that treat the runoff that does occur. Kentucky's guidance states that all surface drainage from disturbed areas must pass through a sedimentation pond or a series of ponds. Adequate measures along with ponds must be installed to meet KPDES effluent limitations. Specific to mine drainage treatment, all strategies have two common goals: neutralizing acidity and capturing and retaining metals. These goals can be accomplished through chemical treatment, aeration, and settling procedures. Treatments for mine drainage must be designed to meet specific chemical and physical characteristics of the mine drainage being treated, which can vary depending on the site's geology, hydrology, and other factors. For the first step in treating discharges with a low pH, the alkaline reagent used to neutralize acidity is selected based on several factors, including its solubility, chemical cost, application requirements, and maintenance needs. Remember, this step also enables dissolved metals to precipitate and settle out. Treatment may be active, the addition of chemicals, or passive, treatment while flowing through a structure. Most treatments are calcium or sodium based. Hydrated lime, calcium hydroxide, is the most commonly used reagent. It can be applied on dry or liquid forms and is relatively inexpensive. It is often used in situations where large volumes of acid mine drainage must be treated over a long period of time. That means greater than 3 years. Crushed limestone, calcium carbonate, is the cheapest reagent by weight, but has limited solubility and lower reactivity at higher pHs. Since it is unable to raise the pH much above 7.5, it is inadequate to assist with the precipitation of most heavy metals. However, passive treatment systems have successfully used covered limestone drainage trenches to treat acid mine drainage in an anoxic state. Quicklime, or calcium oxide, is seldomly used because it forms gypsum in the neutralization process, which can clog discharge pipes. Caustic soda offers the benefit of raising drainage pH above 10, thus fostering the precipitation of manganese. A downside is that it also produces a gel-like ferric hydroxide sludge. Soda ash is most commonly used to treat acid mine drainage that has low flow rate and low acidity. It can be used in solid briquette form as well as a slurry. Some mine drainages are not acidic, so this step can be skipped to move on to deciding how to precipitate and capture the heavy metals. Layers of rock and earth above the coal removed during mining commonly contain traces of iron, manganese, and aluminum, and also contain other heavy metals that can be toxic to fish and other life if the concentration is high enough. For example, iron can destroy aquatic food chain that fish feed on and can clog gill structures of fish. Iron, manganese, and aluminum are the most common metals that need to be removed from mine drainage. Each forms a solid precipitate with an identifying color. Metals may be removed by raising the pH of the water and allowing them to precipitate out as sediments, or by adding chemicals to encourage precipitation. Like with pH neutralization, the method should be selected carefully based on the metals that need to be removed and their concentrations, its effectiveness, availability and cost, and byproducts of the reaction. Iron and manganese are common in groundwater and may need to be removed from solution with the addition of potassium permanganate. Potassium permanganate oxidizes iron and manganese into their insoluble states. Once these metals form solid precipitates, they can be removed by settling ponds or basins. Sedimentation ponds accomplish the dual goals of aeration and settling of mine drainage. The addition of oxygen at the pond surface and the detention time work together in a single pond or multiple ponds in succession. Settling is also possible in a fabricated clarifier structure or in a treatment wetland. These photos show settling ponds with bluish water entering the pond and the orange colored water following the oxidation of ferric oxide. Methods of treatment of mine drainage include active chemical treatment or passive treatment. We will talk about each of these in turn. In a previous slide, we discussed how various chemicals can be selected and applied to neutralize the pH and remove metals. In active treatment, these chemicals are stored in a storage tank and then released into an inflow pipe or a ditch which contains the polluted mine drainage at a set rate. A settling pond is located below the water treatment system to slow down the flow and capture the precipitating metals. Active treatment systems have the drawback of being expensive due to the need to purchase chemicals and supply electricity in perpetuity. Therefore, passive treatment systems are often recommended where feasible. In examining these passive treatment systems, we'll begin with the constructed aerobic wetland. Artificial wetlands are utilized to aerate and settle metals in mine drainage. The microbes in a wetland system can help further remove heavy metals, fixing them in the underlying soils in an insoluble state. They are typically recommended in conjunction with other mine drainage treatment practices. For example, they can become long-term passive treatment installations that receive pre-treated water from settling ponds. Sludge may need to be periodically dredged and removed from these wetlands. The simplest method of passively treating mine drainage is to use limestone rock to line the drainage or stream channel. The limestone dissolves as the rock flows over it, adding alkalinity and increasing the pH. If the drainage contains dissolved metals, they may drop out of solution with the increased pH and aeration as the water moves over the rocks. The solid precipitate can armor the channels over time, reducing its effectiveness. When this happens, the rocks can be mixed around or more limestone can be added to the channel. If the channel is on a steep slope, this armoring or crusting may be less likely, but the treatment may be less effective as the water moves over the limestone more quickly due to the slope. In anoxic limestone beds, high-quality limestone is buried under a liner and soil covering to avoid the interaction of the mine drainage with oxygen from the atmosphere. This treatment is not used with ferric iron or aluminum because it will clog. However, for ferrous iron and manganese, this treatment is effective for increasing the alkalinity of the mine drainage before a settling pond. Drawbacks of limestone beds are that they are difficult to repair and they have a limited lifespan of about 20 years. A drainable limestone bed is simply a pond filled with limestone that includes an underdrain. The limestone treats the acidic water, allowing the metals to precipitate out. Draining the bed on a weekly basis can help prolong the life of this treatment system by decreasing the amount of iron precipitate that crusts on the rocks. An aerobic vertical flow system allows the drainage to pass through a series of treatment steps before the water is discharged. These are also sometimes called successive alkalinity producing systems, or SAPS. First, water flows into an artificial wetland, then filters vertically down through compost layer to remove dissolved oxygen. The removal of the oxygen helps prevent iron precipitate, that yellow boy or crusting, from forming, and coating the limestone the next step, reducing its effectiveness. Then the mine drainage passes through an anoxic limestone layer to add alkalinity. The water leaves through the underdrain, which typically flows into a settling pond in which the iron and other contaminants can be removed. Most of these treatment options have the drawback of requiring a large amount of space, which can exceed the land that's available. They may also not be desirable for private property locations. This has given us a brief overview of the ways to treat the mine drainage, and now we'll transition back over to the second major category, topsoil and overburden handling.
Topsoil and overburden handling addresses the rock and soil that lies above a coal seam. It's sometimes also referred to as waste or spoil. The Mining Guidance Manual provides recommendations for multiple types of topsoil and overburden categories. Handling of these materials goes through many steps, from the initial removal of topsoil to backfilling and grading after the coal is removed, and the disposal of excess or acid spoil. In general, overburden and topsoil should be stabilized and recontoured if needed to conform to the site's topography, then vegetated. Surface waters and stormwater runoff should be diverted around piles of these materials. Topsoil is the richest uppermost layer of soil and should be separated and stockpiled for later redistribution. In some areas, such as the mountainous Appalachian region, topsoil may be less than 6 inches thick. In these cases, topsoil may include the unconsolidated material beneath it to a depth of 6 inches. Ideally, topsoil that is removed from an area of an advanced mining cut should be immediately distributed on land that's already mined. If it must be stockpiled, measures should be taken to stabilize the piles and minimize erosion. For stockpiles left in place for more than 30 days, the establishment of quick-growing annual or perennial vegetation is required. As we've mentioned, spoil refers to all overburden material that's excavated during mining operations. When it can't be immediately backfilled and regraded, temporary storage piles should be located on stable sites with little or no slope. The piles should be located in areas that don't have seeps or springs or poor drainage and located to minimize handling distances and costs. Additionally, diversions should be created around the spoil storage sites, and all storage areas should drain to a sediment pond. Backfilling and grading refers to the procedures that are used to replace spoil into the pit or onto the bench and grading it to approximate original contours. Backfilling and grading procedures include eliminating high walls and spoil piles and dewatering of the mining pits. By conducting these activities as the mining is occurring, you can better ensure stability and safety of the areas, minimize soil erosion and water pollution, promote revegetation, and restore hydrology. Within 30 days of backfilling and rough grading, the area must be final graded, scarified, topsoil redistributed, and seeding completed. Extremely compacted soils often result from the use of heavy earth-moving equipment. Surface roughening or scarification is critical to ensuring water infiltration and root penetration on reclaimed land. If possible, roughening should be done on the contour to minimize erosion. On steep slopes, a dozer can be driven up and down the slope to create cleat or track marks that can aid in reducing runoff, soil erosion, and seed loss. Prior to scarification, lime may need to be applied to soils to raise the pH to a level that's needed for establishing vegetation. The identification and selective handling or burial of potentially acid or toxic forming spoil is a crucial measure to protecting surface and groundwater quality. This helps prevent the formation of acid mine drainage. This slide lists several ways that acid spoil can be handled, including mixing it with other overburden materials, burying it with these materials, and treating it with limestone. Once all these measures are complete, the usual method of disposing of excess spoil remaining is to place it in engineered earthen and rock structures known as head of hollow fills, or valley fills, which are stabilized with drainage controls. A sediment pond is typically installed downslope of these valley fills to collect runoff and allow settling of particulates. Kentucky's Division of Abandoned Mine Lands is charged with protecting the public from health and safety problems caused by mining that occurred before 1982. These dangers may include landslides, water-filled pits, open mine portals, and dilapidated equipment and buildings. AML restores these sites to a safe and environmentally stable condition through reclamation activities. The AML Division also administers a bond forfeiture program. Before a company begins mining, they are required to post a reclamation bond. If the company fails to mine and reclaim the site to the standards specified in their permit, the bond money may be forfeited to the state. These forfeited funds are used to reclaim the site. AML has also overseen a recent pilot program to distribute federal funding for reclamation of AML sites in conjunction with economic and community development and reuse goals. You'll learn more about this program in Module 5 when we hear from likely partners. But you should be aware that it is a potential source of funding for watershed improvement projects that assist with the economic development goals of this pilot program. We're going to end this section with a few case studies that may be of interest to you. The first is in Pike County. The Octavia Church AML project reclaimed a refuse area of approximately 6 acres. It threatened the nearby Octavia Church as well as motorists on the adjacent roadway. During heavy rains, coal refuse washed into and blocked the roadside stream, causing sediment and water to flow onto the road, which increased the risk of accidents as well as increased the maintenance needs on the roadway and at downstream culverts and bridges. It also caused downstream water quality impacts. Through the AML reclamation project, an existing sediment pond was cleaned out and the dam spillway was repaired. A berm along the edge of the creek and diversion ditches were lined with rock or erosion control blankets, and they routed runoff to the cleaned out sediment pond. Coal refuse was removed from the creek banks and sold at marketable value. Then the area was covered with topsoil to at least 2 feet deep. Drainage was further controlled with additional hay bales, berms, and diversion ditches, and the whole area was revegetated. Another notable success story was in the Rock Creek AMD project in McCreary County. Acid mine drainage from coal mines had decimated aquatic life in a 4-mile stretch of Rock Creek. The upper portion of the creek was considered a wild and outstanding natural resource water, but the lower portion was suffering from acid mine drainage from over 40 coal mine portals and coal refuse dumps, which severely impacted aquatic life. This lower segment was listed on the 1990 303D list for non-supportive aquatic life and swimming. Best management practices installed in the Rock Creek watershed included removal of coal refuse from the stream bank areas, open limestone channels, and a vertical flow wetland system. Water in the creek was further treated for acidity with limestone sand. A 319 grant provided funding for the construction of the open limestone beds and the removal of coal refuse from the stream banks. Other funding was obtained from the Appalachian Clean Streams Initiative, Eastern Kentucky Pride, Kentucky AML, and the USGS. All of these practices decreased acid and sediment loading to the creek and enabled areas that previously could not support fish to host diverse fish populations. The final project we wanted to mention is especially creative and serves as a great teaching tool for the public. The 35-acre AMD and Art Park is located in a mined area of southwestern Pennsylvania. The AMD, or acid mine drainage, flows into the park with a pH of 2.8 and exits at about a pH of 6.5. One section of the park is devoted to the wetland treatment cells and ponds of the AMD treatment system. An accompanying litmus garden functions as a visual representation of the changing acidity of the water. As the water moves through the treatment system, it undergoes a visual transition from the red-orange of the AMD to the blue-green color of clean water. Small groves or bands of 13 native tree species were chosen for their autumn foliage colors that turn deep red around Pond 1 and grade through orange and yellow to blue-green at the end of the treatment system in Pond 6, creating visual reflection of improved water quality. Another area called the History Wetland educates about the site's previous use as a coal mine. And another section is being developed as a recreation area with sports fields and a pavilion. You can find much more information about this park online, including funding sources and all the partners involved. Finally, we wanted to mention this supplemental resource from the West Virginia Department of Environmental Protection. It provides some helpful guidance for watershed groups who are looking for ways to proactively address mine runoff problems.